It's time for round two. My second project, this project is another decentralized application, but my priority is a little different. These starter projects are often less robust and convenient for user and developer, but I wanted to start building things that made sense for users and developers to switch to and use my project over other centralized systems. So my intention and my first priority with the second project is real world contexts. There's a lot to this project, and I go really in depth into each of those components in my two-part article that I've written and linked below. But here's a brief overview and an insider view into my latest decentralized application. The two backbones of a decentralized application are scripts and, of course, the smart contract. You technically only need these two things to create a sort of functional backend for an application that users can interact with. But my application at its core is a funding smart contract. And just with a few tweaks and changes to its front end, it can turn to services like crowdfunding, escrow services, charity donations, and employee payroll, or some sort of staking reward system as well. I wanted to build something that made sense in the real world. So I made sure that this app was effective and functional for a user to use, but still convenient and robust for a developer like me to build. So there are these advanced tools and techniques that you can use in blockchain. And the ones that I leveraged in this project specifically were price feed oracles, unit and stage testing, and gas optimization techniques. But instead of throwing around these random technical words that are supposed to do something, let's just take a look at my code. One more thing before we get started though. What's the hype with these smart contracts? In short, the power of smart contracts lies in their ability to unlock new levels of trust, transparency, and efficiency in our global economy, paving the way for a more decentralized, democratic, and equitable world for everyone to live in. But this is the dramatic or non-technical definition of a smart contract. In technical terms, a smart contract is a self-executing program that runs on a blockchain network. It's really just a set of rules or instructions that are written in a programming language, for example, Solidity for Ethereum, that are stored on this blockchain and are executed automatically when certain conditions are met. Not only do they not need any human input, but smart contracts are also designed to be immutable. So once they're deployed to the blockchain, their code cannot be changed, instilling an even deeper layer of trust that just can't be replicated on centralized systems. Let's see what's going on in this smart contract of mine. So this contract is called fundme.sol. First, all I do is I just initialize the license, the Solidity compiler that I want to use in this contract, as well as some imports. A really important one that I want to highlight is this priceconverter.sol contract console library that I import, because this is what lets me access the Oracle data and the Oracle network that I want to leverage into my application. And then here is just an error that I use sometimes as an alternative to console.logs because they seem to be taking less gas. So it's a small gas optimization technique because I seem to be really obsessed with these console.logs. Anyways, moving on, I have a declaration here of this price converter library. And again, this is what's going to let me leverage those price feeds and the conversion rates between ETH and USD that I really wanted to incorporate into my application. And then are some state variables that you'll see me mention over and over again in this contract. Funding, to start off, I restrict some functions to only the owner of the contract. For example, the withdraw function, which should only be for the owner in my use case of the application. And then I initialize the contract and the price feed that needs to be used. The aggregator v3 interface is a tool that Chainlink provides and essentially is a combination or a whole library of price feeds. And then it is modularized based on the chain that I'm on or the chain that I'm working with. So it's super convenient that I have that there. And then these receive and fallback functions are a little special as well. So the fallback function allows a contract to receive and handle Ether transactions. And the receive function is called when the Ether is sent to the contract. So essentially in a sample scenario, the fallback function is called when the contract receives a call that is not matching with any other function in the smart contract. With all that done, let's move on to the more exciting parts of this contract, which are the function fund and the function withdraw. And those are pretty much the basis of my application. It allows users to contribute to the contract. So it checks that the amount of Ether sent by the user is greater than or equal to the minimum USD amount that I declare up here somewhere in a variable. It also adds the user's address and the contribution that they have to the s_address to amount funded, and then the s_funders array as well, respectively. So those are just two variables that store information. This function over here just lets me get the version or fetch the version of the price feed that I'm using, so not too important. And then is the withdraw function. There's two here, the cheaper withdraw and the normal withdraw function, but I just talk about the normal one here, and I'll talk about the cheaper one when I get to gas optimization. The withdraw function, regardless, allows the contract owner to withdraw all the funds that have been deposited into the contract by its funders. Initially, the withdraw function iterates through the s_funders array right around here, and this is what contains the addresses of all the funders that have contributed to this contract up till this date. And then for each funder in the array, the function sets their funding amount to 0 in the s_to amount funded mapping, and then the s_funders array is also reset to an empty array. The contract owner is now finally able to withdraw all the balance that the contract has right now using the call function at the very end. That's actually about it for my smart contract. It pretty much sums up the functionality of it. Of course, if you guys want more detail, you guys can check out my article below that really goes through each line of code. Another tool that I used and really experimented with in this application were those price feeds. I was able to retrieve and calculate the price of Ether in USD using a chain link price feed library called aggregator v3 interface. And this is what has access to all those Oracle networks and the Oracle data. So I created another contract-like file called priceconverter.sol that you can see right over here. And although it is written in Solidity, it does not necessarily serve the same purpose as a smart contract or have the same functionality of it. And I can still establish functions within it to start to leverage the data from the Oracle that it has access to. So the get price function over here takes an input parameter price feed of type aggregator v3 interface. So this parameter represents a price feed contract that is used to get the current price of an asset. So within the function, there's another function called latest round data, and it's called on the price feed as well, which returns many things, but mainly the answer value that we're really interested in. And this is what represents the current price of the asset in question. Lower as we go down, the answer value is then multiplied by this large number and is cast to a uint256 variable. So this value is returned by the function actually as the price of the asset in question, but this time denominated in USD with 18 decimal places. And that's just the number of decimals that ETH and WEI have, so that's why we need to do that calculation with the large numbers. The get conversion rate function right below it, right around here, takes two input parameters: ETH amount, which represents the amount of Ether to be converted in USD, and then price feed, which is the price feed contract that represents the current price of Ether in USD. So it's very real time and updated by the Oracle. So within the function, the get price function is called with the price feed parameter to get the current price of Ether in USD. So this value is then multiplied by ETH amount and divided by this large 1 to the power of 18 number, which is the number of WEI in 1 Ether. So WEI is the smallest denomination of Ether as the currency. The resulting value represents the USD equivalent of the ETH amount parameter. The value is returned by the function later on in the lines as a conversion rate of ETH amount Ether to USD, and based on the current price of Ether provided by that price feed parameter, which is essentially just the Oracle network. So I just got the current price of Ether in USD provided by this price feed parameter from the Oracle that the library has access to, if that makes any sense. So this library is essentially just a reusable piece of code that can be called by my smart contracts, and it can perform specific functions or tasks that I want it to perform. So we're done with smart contracts, and this is what seems like the entirety of Web3 development and Ethereum's protocols and all the craze that comes with it. But in order to execute them, specifically their functions, you need to write detailed scripts that have instructions for that smart contract. So of course, I import all the libraries and tools that I need, and I just want to highlight this helper hardhat configuration file that I import because it's really important as it has all the price feed information that I need, so I can switch to any price feed depending on the chain that I'm on, making the entire process really automated. I'm going through with the deploy function. So I have the correct price feed, I have the deployer object that lets me deploy it, and then I wait for a couple confirmations after the smart contract is deployed. And at the very end, I'm able to verify this deployed contract on Etherscan. If it is not a development chain and I do have an Etherscan API key that's provided in another file, which is usually the configuration file, I would be able to verify this contract on Etherscan, which is super fun because I can finally see my hard work paying off in real time. So at the very end, it's not too important, but I specify the tag for the deployment script. So I'm just more specific in my terminal. It's a small trick that I learned to make sure I'm only using the scripts that I want and only deploying the things that I need to be deploying. But overall, that is the function of this very simple deploy script. Other than the deploy script, I also have two other scripts that I've written in my application, and those are the fund and withdraw. So let's take a look at what exactly this fund script is doing. In general, the code deploys my smart contract FundMe and funds it with 0.1 Ether defined in weight. And of course, I can change this amount whenever I want from my front end as well. So just to get started, the await get named accounts function retrieves the Ethereum address of the predefined deployer account that I already get from Hardhat, since I am deploying to a local network that Hardhat provides. And then the get contract function creates an instance of my contract, my FundMe contract, using the contract's name and the deployer's address. Now, the fund function is finally called after that. It's called with a value of 0.1 Ether since I have defined that from before. And then the transaction response wait function waits for the transaction to be confirmed on the blockchain. And once all of that is complete, the main function can finally run. It just makes sure that everything is completed successfully. And if it is, the process is completely terminated with an exit code of 0. I kind of jump around a bit in this code because there are a lot of await keywords here, as you can see over here and over here. So if you guys are a little bit more confused about async functions, just like how I was, you can definitely check out my article where I try to explain them to the best of my ability. But other than that, that is the final summary of the fund script. This is another super clear and concise script literally meant for one thing, and that is to withdraw. So this asynchronous function retrieves the deployer's address using the get named accounts function. This case would be the user's wallet that is connected to my website that I have also made. This get contract function creates an instance of the FundMe contract using its name and the deployer. So you can see a lot of similarities from the fund script that I just showed you guys earlier. And then this console.log just lets the user know that funds have started to be withdrawn, since I do call the withdraw function that I first initialized in my smart contract. And then after I wait for everything to be confirmed, I finally console.log that all the funds have been retrieved back into my account, and this function was successful. This last main function, of course, is always run as well at the very end and just terminates the entire process with an exit code of 0, making sure everything was confirmed. And that is the gist of this withdraw script as well. I also mentioned the term gas many times in this video, once with those error messages and again when explaining those libraries. So every operation that a smart contract performs costs a certain amount of gas. And that is a unit of measurement for the computational effort required to run that specific operation. The gas limit is set for each block in the Ethereum network. And if a transaction exceeds this limit, it will actually fail. So you do have to be mindful about the amount of gas that you're using in your development. Other than ensuring that you're under this gas limit, these techniques, these gas optimization techniques, actually help to reduce the time it takes for a transaction to be confirmed and included in a block. This is because miners are incentivized to include transactions with lower costs. So reducing usage can make a transaction more attractive to miners as well. That's why there's a reason to optimize for gas in a real-world context and real-world development. And that's why it was my priority in this project specifically. Now that we understand the concept of gas, let's take a closer look at why I'm on this page in the first place. This is essentially a GitHub repo, and it represents Ethereum opcodes, or all of the operations that can take place on an Ethereum smart contract specifically. Here we can see the operation, and on the right is the corresponding amount of gas that each operation takes up. We can scroll down and see that they are all relatively low and relatively the same until we get to 820,000. So these are the gas amounts that are required to load words from storage and save words to storage. We know that things get really pricey when we want to work with these operations specifically. We can take a look at my smart contract actually and see that I've appended these storage variables, these really pricey ones, with S. So S underscore price feed, S underscore funders. This is so I know that I'm working with something really expensive and I need to be mindful. I've also appended the immutable variables to I underscore owner, or whatever the variable name is called, and then constant variables to constant. So I know exactly what I'm working with and if there's a way to make it even cheaper. Let's see what's exactly happening here before we take a look at the code. Overall, the gas fee is first paid by the user who initiates the transaction or contract function and is denominated in units of gas. The gas price is set by the user and represents the amount of ether they're willing to pay for each unit of gas. And then that total gas fee is calculated by multiplying the gas price by the amount of gas used to execute the transaction or whatever function there is on the contract. Lastly, the gas fee is finally paid to the miners who process and validate transactions on the Ethereum network as a reward for their work. Let's take a look at the code now. This withdraw function seems to have a lot of those S appended variables. So this is where we're working with a lot of storage. First up in this function is a for loop, which means every time we go through these sections, we're looping through and working with all of the pricey variables each time. We're comparing in this sense if the funder's index is less than the S underscore funder's length in storage. It's appended with that S name or that S letter. So the longer the funder's array is, the more times we will read from storage and more gas will be used. That is a crazy amount of gas, guys. Second, right underneath that, we're reading a lot from storage and saving this data to the address funder memory variable. But then we're also updating the storage each time. You can see that over here. So it's just this section that's taking up a lot of gas. With this cheaper withdraw function right underneath that I've already written out, there's one major change. And that's that we're reading the entire funder's array into memory first, and then we're accessing the indexes to make whatever comparisons we want from memory each time instead of from storage. So instead of that S underscore funders array. We can now read and write from the memory variable and only update storage when we're done with everything. And that is what makes such a big difference with gas and the amount that we're using in our smart contract. I went ahead and tested both of these functions on a local network and a testnet, as well as with a one funder scenario and a multiple funder scenario. But regardless, you were always better off using the cheaper withdraw function as it saved you around 3.70 cents. But if we look at the max values, we can start to see the huge difference in gas and actually see that it's worth doing all this extra work. Again, this is just one scenario that I decided to highlight to show how I optimized for gas. But it's these layers of logic that you can add to your application that make it efficient, robust, and so much cheaper to build in the real world. I talk about these price feed oracles enough already in my video, but just for an official explanation, a price feed oracle is a trusted source of price data that gives real-time information and updates for assets like cryptocurrencies. So in my case, I use the oracle to fetch data and update price specifically on-chain. But I first established that contract console library that I've already talked about, and it was called the priceconverter.sol. But let's see exactly how I used it and leveraged it in my smart contract to access that entire Oracle network and all the data that it has. The price feed is specifically involved in the deploy script by providing the ETH to USD price to the deployed FundMe contract. So this address of the price feed is actually obtained from a configuration file that is not in the script and is depending on the current network. So I can show you guys how that looks. It's essentially just a network, and it tells you the network name as well as a corresponding price feed from the Chainlink library. And this is so the script can access any of the information when it needs to. And then the obtained address is passed as an argument to the FundMe contract during deployment. It's as easy as that. The FundMe contract uses the price feed to convert ETH amounts to USD specifically for funding requests. Without a price feed, the contract would not be able to accurately calculate the USD value of ETH amounts received, and none of this would work the way that I would want it to. Last, the price feed is involved in the fund function of the FundMe contract as well. So the required statement in the fund function uses the price feed to determine if the amount of ETH in USD sent with the transaction is sufficient for funding. Specifically, I use the get conversion rate function of the price converter library that I've imported, which is the price converter.sol that you see up here. And essentially, it uses the price feature to convert the amount to its USD equivalent. If the USD equivalent is less than the minimum underscore USD constant, which is in all caps there, that is set to 50 ETH in USD. So if it's less than that, the transaction reverts with an error message indicating that the sender needs to spend more ETH to even start funding the contract. I don't know why these tests excite me so much, but I think it's because I'm finally using an advanced tool for real-world blockchain development. Now, I can definitely just deploy the smart contract using the script that I wrote earlier, but it's those extra layers of bulletproof logic that sets an application apart. There are two types of tests, staging tests and unit tests. Staging tests are more end-to-end, testing for the holistic or entire application, as well as external things like wallets and exchanges that they're a part of, or other random contracts on the same blockchain. But unit tests account for all possible scenarios and outputs of each function in a smart contract. Again, if you guys want more of a detailed explanation, be sure to check out my article. But let's quickly go over what's happening in this unit test of mine. So this first block over here that I've highlighted just checks whether the current network's name is included in an array of development trains. And then if it isn't, the entire test suite is skipped using the describe.skip method. Otherwise, the test suite for a contract named FundMe, which is my contract, is executed, and all the tests will be run. This is a constructor function test, and essentially it checks if the constructor correctly sets the address of the price feed and verifies that the returned address matches the address of the mock v3 aggregator contract that I obtained from Chainlink, and this was also set up in the block above if you want to take a look. So the assert.equal statement is used to compare that actual value returned by the getPriceFeed method to the expected value from the mock v3 aggregator.address method. So the test will pass if they are equal, but if the addresses do not match, some sort of error or something going wrong in the constructor code that needs to be fixed before any of the other tests can run. Next up is this really large fund function test, and it's super important because it's one of the largest aspects of my smart contract and application. This first test over here checks that calling fund or the function fund with no value or insufficient value reverts the entire transaction and returns the expected error message that you can see over there. And then the second test checks that the amount funded data structure is updated correctly by calling fund with a valid value, then calling the get address to amount funded to retrieve the amount funded by the deployer's address that first funded the contract. It then checks that this amount matches the expected value, and if it doesn't, the test will fail. And then last, this test over here checks that the funder's address is added to the array of funders by calling the fund function with a valid value again, and then calling the get funder to retrieve the address of the first funder in the array. It checks that this address matches the expected value of the deployer's address, and again, if it doesn't, the test will fail. Alright guys, this is the last and final test of my application that checks for all the scenarios of the withdraw function specifically. So this first test over here that I've highlighted checks whether a single funder can withdraw their funds from the contract. It first gets the starting balances of the contract and the funder's account, and then it checks whether 1, the contract's balance is 0, and 2, whether the funder's account balance has increased by the amount they initially funded the smart contract with, plus any transaction fees that incurred during the entire process. Next up is this really large test, but essentially what it does is that it checks whether multiple funders can withdraw their funds from the smart contract this time. It first funds a contract with multiple accounts and performs the same steps as the previous test case that I mentioned earlier, or just now. And then it checks whether the get funder and the get address to amount funded functions return the expected values after the withdrawal. Last is this smaller test, but essentially it checks whether only the owner of the contract can withdraw the funds. It tries to call the withdraw function using an account other than the owner, and then it of course expects the transaction to be reverted with an error message. If it doesn't, then that means there's something going wrong here and I need to recheck where the problem is. As you can see, you need to understand this logic behind each scenario to be able to account for all of them. It's this type of creativity and critical thinking that really excites me about these boring tests. But of course, there will always be a more effective way to write them. And I think this is what motivates me to keep iterating on my work and understanding the logic behind it. I'll first connect my wallets and I'll put in the amount of money that I want to fund the smart contract with. After clicking the button Fund, I can confirm my transaction using the MetaMask extension. Looking into Inspect, we can see that this transaction has completed mining, and I can now get the balance of that contract. It's now worth $80 USD. I can also withdraw all of these funds by clicking the Withdraw button and confirming my transaction once again through MetaMask. The balance is now $0. That's about it, everyone. So in this video, I go over smart contracts and scripts, but also things like contract console libraries, gas optimization techniques, some tests that I use in my programs, as well as oracles that I leveraged in this project. Everything that really prepares me for real-world blockchain development. And I'll be honest, this video really helped me fundamentally understand my project and how everything just comes together into one piece. Stay tuned for my next project as well, and stay updated on the strides of progress that I'm making in the Web3 world. Thanks, everyone. Bye.